Resuming our discussion of oscillations, and of course we'll start from where we left off. uh, Oscillations, we discussed what oscillation means. It's a to and fro motion about a mean position, and sometimes we refer to the mean position as equilibrium position. So if an object repeatedly comes back to the mean position and moves along a line and continues a to and fro motion, we uh, we say that it's oscillating system. It may be a pendulum moving about its equilibrium position. It may be a mass attached to a spring. Sometime it's in the horizontal direction that the oscillation is taking place, sometime along the vertical, but it is up and down or sideways. So both ways it's fine. Uh, all oscillations are not simple harmonic motion. For simple harmonic motion, there are two conditions to be met, and we discussed those two conditions, which are in the statement of the definition of the simple harmonic motion. Let me remind you what those conditions were. It stated that in simple harmonic motion, it's an oscillatory motion in which the acceleration is directly proportional to the displacement, and it is always directed towards the mean position. So mathematically, we represent simple harmonic motion with the help of an equation which is A is equal to minus omega square x. I always refer to this equation as the standard equation of simple harmonic motion. So we'll continue our discussion from this point. The significance of this equation is already clear because we showed that all systems that obey simple harmonic motion, that execute simple harmonic motion, obey this equation, and we can always derive an equation for their motion like this. Their acceleration, which is a variable, it depends on what is their displacement at any instant. Where they are depends, decides that what their acceleration at that point is. And we also discussed that this omega is constant for each oscillating system. It is unique expression for it. We learned that for simple pendulum, we derived the expression for omega to be L over G under root. We derived it. Similarly, for a mass spring system, omega has its own unique expression, that was K over M under root. Now we are going to discuss yet another system, and that was one of the past paper questions in October number 14, in which they have given you the equation of that simple harmonic motion in this form, and they have asked you to derive the expression for omega, then for time period and frequency, and let's do it together. And after that we move on to a different topic. Suppose they inform us that we have a certain curved surface like this, and there is a spherical object, let's say a marble, and that is rolled on this surface, and it repeatedly comes back to its equilibrium position this. At any instant, that ball is here, and it can be seen that the separation has a certain value, and we label this separation as x. So x is its displacement. It may be its position at any instant. What is given in the question is that acceleration of this object is given by an expression minus g over r into x. This expression is given in the question, and they have informed that this g is the same acceleration due to gravity. This r is the radius of this curved surface. So these values may be given in the question, but we are to derive an expression for the expression for time period t. This is to be derived. So the first step, of course, is that we compare this given equation with this standard equation for simple harmonic motion. What is obvious from this comparison is that omega square is g over r, because this acceleration is this acceleration. This minus sign is also here in this equation. X is also playing the same role in the two equations. So what is compared and what can be inferred from this comparison is that omega square must be g over r for this particular system of oscillations. This readily means that omega must be equal to g over r under root, which means 2 pi over t. Or let's say we talk about, so an expression similar to one we derived for the simple pendulum. It was the length of the pendulum here, if you remember, and the rest of the expression was the same. So if they give us the values of radius, it is easy to calculate the value of the time period of the oscillating system of this type, in which a circular object is oscillating on a curved surface. So this is one significance of this equation, in which we can compare it with other given equations and find the expressions for frequency and time period. What is the significance of this equation? In another angle, from another angle, we'll see there are many questions in which this same equation is used. And that is when we are required to draw this acceleration against this displacement. We can see from this equation that with different values of x, we have different values of acceleration at different positions during the oscillation. As the object has larger displacement from the mean position, the value of acceleration is increasing. So that means it is possible to draw a graph between the values of displacement and the resulting acceleration from it. So what we see is we have a graph of this type in these situations. Of course, this graph stops at a certain value of acceleration that corresponds to a certain value of x. So we take x on this side, we take acceleration along this. If it's a certain system of oscillation which is executing simple harmonic motions, but we are not sure. But when we plot a graph and we get a straight line which is passing through the origin, which has a negative gradient, it's a straight line. this is enough to uh, to infer, to deduce that the system is executing simple harmonic motion. Suppose this is not exactly what we know about the system. All we know is that when we plot a graph between various values of x and we get a straight line passing through the origin with a negative gradient, that means the system is undergoing a simple harmonic oscillation. So there are so many questions in which you will uh, actually plot this graph either, or if this is already given, you have to explain why this graph is sufficient to deduce that this system is executing simple harmonic motion. Let me write this as a question. Explain why this graph shows that the system is undergoing simple harmonic motion. So there are a few points that you will write in your answer. Suppose this is a question for 4 marks. In one of the possible questions, this graph is given and they have asked to write the answer to this simple statement, that why do you think on the basis of this graph that the system is executing a simple harmonic motion. It's a 4-mark question. So in these 4 marks, what do they want to see in your answers? They want to see, number 1, it's a straight line. It is a straight line through the origin. That means the proportionality is intact. If there are 2 quantities plotted against each other and the graph results in a straight line through the origin, that means the proportionality part is confirmed. But what about this negative sign? This means it is negative gradient which confirms that acceleration and displacement are opposite in directions. As I emphasized in my discussion of this equation, that when acceleration is towards the center, displacement is in this direction, and when acceleration is in this direction, x is negative. So in all the cases, whether the object is moving to the extreme or moving towards the mean position, acceleration and displacement have opposite signs in the 2 cases. So that is why this negative sign, and that simply means that acceleration and displacement are opposite. So these are the 4 points that you will always include in your answer when they ask a question like this. Yes, if it is not 4-mark question, maybe it's sometime it's 2 mark, sometime 3, then either 2 or 3 points will be sufficient. One point about this shape of the graph that I can also mention before I discuss displacement time graphs. If this is displacement and acceleration plotted against each other, you can readily see that gradient of this, gradient is omega square. That means if you are provided with this information, with this graph, you can calculate omega, and from omega you can calculate the frequency, and from frequency you can calculate the time period of oscillation. So one significance of this graph, which confirms that the object is undergoing simple harmonic motion, is that you know its angular frequency, you know its frequency, and you know its time period. So there are questions. I'll share a question or two with you in the worksheet tomorrow, and then you will understand how you will do it. For now, we are moving on to one important topic, and that is displacement time graph. Another related topic, displacement time graph. You have studied displacement time graph in O levels. You studied displacement time graphs in the AS, and most of the time they were straight lines. And if they were curves, you did not have to elaborate mathematically what that curve signifies, where its value is given by what formula. So things were simpler. But this time, we use an equation to describe what this displacement is at a certain point, depending upon what is the nature of its variation. Displacement is one variable during the oscillation, velocity is another variable during the oscillation, acceleration is another variable. So we'll discuss these variables one by one. Displacement varies with time means when you start observing an oscillation, let's say this is the system in which an object is oscillating on a curved surface, it repeatedly comes back to this mean position. Suppose initially it is at this extreme, and we allow it to roll down, it comes to this position, but doesn't stop here, it moves to this extreme, and then it comes back to the mean position, goes to the other extreme then, and it continues like this. What is the expected shape of the graph of displacement x with the time? So if I start from the extreme position, this is going to be the position of this graph. And this is the sinusoidal variation of displacement with time. At t is equal to 0, the object is at its maximum distance from the mean position on this side. So its displacement is this one. Whatever its value, this is its amplitude. So from this graph, one quantity that you can readily see is its amplitude. And let's label it as x naught. X with a small 0 attached to it. That means this is the value of displacement when t was 0. So x naught is usually the symbol we use for its amplitude, the maximum displacement from the mean position in the beginning. But as the time goes on and it continues to oscillate, it repeatedly comes back to the mean position and goes to that amplitude, the maximum displacement from its mean position again and again. This is the graph that results from it. And if there are no resistive forces, the object moves without any opposing forces acting here. The amplitude does not vary. It maintains its amplitude over a long period of time, but eventually there are opposing forces, there is friction present, air drag is playing its role, so its amplitude gradually decreases. So that is something we'll refer to, we'll come to it later on. The second quantity that can be readily seen from this graph is what is the time period of its oscillation. What time it takes to come from this position to this, then to move to this position, and then come back to where it started. So if it started here, it goes to the mean position where x becomes 0. It goes to the other extreme where you have minus values of the amplitude. Then it goes to the mean position where x drops to 0 again. And then it goes back to where it started. So this is where it completes its oscillation. So if this position is A, and this position is C, and this is B, it is easy to see from this graph at what instant it is at C. And at C, it is for 2 times during one oscillation. So this is the time when it passes through C for once, when it moves to this extreme, and when it goes back to it, this is another point when it is at C. And this is the instant when it is at this extreme, which we have labeled as B. So it is at B here, it is at C here, it is at C here, and it is at position A again, and this is the same position where it started. So in the oscillatory motion, we need to understand from this graph where that object is, at which particular instant, what is its position during the oscillation. So it started from the extreme position A, and it rolls down to position C when its displacement is 0, which means it is at mean position here, and then it rolls up to this extreme that we have labeled as B, and that is the instant. You can read here from the graph what instant it is when it is at this extreme. And when it rolls down to C again, it is this position, this instant, and then it doesn't stop there. It rolls up to the other extreme, the same point where it started. So one oscillation is completed during this time, so we label it as capital T. So this is the time period. This is not wavelength because we don't have any distance on this graph. This is time. So when we have time here, let me remind you, we studied displacement time graph, and I emphasized this point there, that when we have time here on this axis, the difference between these two crests on the wave is not wavelength, it is time period. So same is here. That means we can readily see what is the time period for this oscillating system. And if values quickly, and there are questions in the exam in which we but there is at least one equation that governs this change, and there are questions in the exam in which they give you that equation, and you need to understand what each quantity means in that equation, and that is x is equal to x naught cos omega t. This equation represents this motion, which clearly means that at t is equal to 0, this cos 0 gives us 1. So our displacement becomes x is equal to x naught. So at t is equal to 0, x is equal to x naught. But as we move further, there are values of t where this omega t turns out to be pi by 2, 90 degree, and in that case cos will become 0, so x will drop to 0 here, and then there will be values where x will come out to be minus x naught or any other value of minus x. So with t varying, x will have various values, and this is the manner in which it varies. If we start this graph from the mean position instead of extreme position, this equation could be x is equal to x naught sine omega t. I hope you all understand that simple fact, and let me quickly make it here so there is no doubt left. For a system which is initially at the mean position and then its displacement varies in this manner in time, its equation is given by x is equal to x naught sine omega t. But in either case, it is the time in which x is varying. Now at t is equal to 0, sine will be 0, and sine 0 is 0, so x is equal to 0 in the beginning. So the two equations are used to represent what is the value of x at any particular value of time, at any instant. In both cases, this number will always mean the amplitude, and this omega is used to calculate the time period and the frequency of the oscillating system, because in both cases omega is 2 pi f, or which is mean, which is equal to 2 pi over t. So values of frequency and time period can be readily worked out. I'll share with you some questions tomorrow. I'm not giving you a worksheet today. All you need to do is go through all this and try to familiarize with yourself the kind of questions you have in the exam. When I have discussed these type of questions in more detail tomorrow, you will be in a position to attempt the worksheet that I'll share with you tomorrow. Thank you for today.